Okay, so let us start our class today. Today we're going to look at chapter 11. Chapter 11 is just a very short chapter, and we are supposed to use 2.5 hours to complete it. But I believe we can finish it within an hour. Okay, because it's more on memorizations. You're going to memorize the definitions of stress, strain, stress, energy. You're going to memorize the shape of a graph and then understand what does it mean by the every part of the graph. Okay, so first, okay, order solid may be thought as having a definite shapes and a volume, and it is possible to change its shapes and volume by applying external force. Now, all solid, we can change its shapes. Just depends on whether we change a lot or just a bit of its shape. So, a sufficient large force will permanently deform or break an object. But otherwise, when an external force are removed, the object it tends to return to its original shape and size. So this is what we call elastic behavior. Okay, so the elastic properties of a solid we discussed in this chapter we call stress and strain. Okay, we're going to look at these two terms today: stress and strain. So consider a long bar cross section area A and a length L node. Climb at one end when external force is applied along the bar, okay, perpendicular to the cross-sectional area. The bar extend by an amount of elongation. So elongation is also the extension. Okay, it's also the extensions of the object of the solid object. So figures a figure shows a bar climb at one end is stretched by an amount of E. So this E is not your electron, it's not your elementary charge, it's the elongation. Okay, don't get the wrong idea. Sometimes students they substitute the wrong value because in the list of formula you also have this E, but this E is known as elementary charge. Okay, the values of the charge. So the elastic property of a material, it is an important criteria to determine the strength of a material. Okay, it measures the tendency of the object to return to its original shape after you remove the force, which is the stress on the object. So this chapter we are going to focus on elastic property. Okay, we want to see whether an object managed to return to its original shape or not. Okay, if not, what is going to happen? And what is going to happen if we exert too much force on the object? And so on. And we're going to look at various types of object as well. So what is a stress? Stress is defined as the ratio of the magnitude of force to the cross-sectional area. Okay, where the force vector is perpendicular to the cross-sectional area. So force vector is perpendicular to the cross-sectional area. Now, what does it mean? So just as shown in the diagram. So we have an object. Okay, we have an object. The cross-sectional area is here. Okay, the one in the red color. Now I just color it. So this is the cross-sectional area. So the force that you apply along, okay, perpendicular to the cross-sectional area. So you remember the area that we use, okay, is always perpendicular to the force, right? It's always perpendicular to the force. So don't use the wrong area. So area always perpendicular to the force. So in this case, the equations, now stress, the symbol is a sigma. So sigma is equals to F over A. Okay, F over A. So this is the equation. So force perpendicular to the cross-sectional area. So area is the cross-sectional area. Okay, you chop it off. So you take the area of the object. So the unit is kgm negative 1 s negative 2 or nm negative 2 or sometimes we just call it Pascal. So it is a scalar quantity. Okay, so stress is a quantity that is proportional to the force causing the deformation. So the higher the force, okay, the more force you exert on the object, then the more deformations. Okay, the object will deform more compared to a less force. And then strain. So stress, we talk about force. Then what is a strain? Strain is the ratio of the change in the length, which is what we call elongation, to the original length. Okay, to the original length. So in this case, we can say epsilon equals to, now you're looking at elongations, the ratio of elongations to the length. So E over L naught. So at the same time, we can also write it as delta L, the change in the length over L naught. Okay, so basically you have two equations that can be used to calculate it. Now basically the two equations, they meant the same thing. Okay, just that we use a different term. So delta L is a change. Okay, change in length. So sometimes it's not just a extension, okay, it's not just an elongation. Sometimes when you compress the object, okay, so there will also be a change in the length. So in that case, that is also what we call strain. Okay, it can either you stretch it or you compress it. Okay, compress it. So both will cause a strain in an object. So now the result of a stress is a strain. Strain is a measure of a degree of deformation. So it is a dimensionless quantity. Why dimensionless? Because you are using length divided by length. Okay, length divided by length. So stress, it tells you how much it deformed. Okay, what is the relationship between the force and the deformation? And strain, it tells you the degree of deformations. Okay, now this is a very important graph. You need to know how to sketch the graph. You need to know which part of the graph represents a elastic deformation, which part of the graph represents plastic deformation. All right, sometimes questions will ask you to sketch this graph, and then after that, you need to be able to explain every part of it, okay, the meanings of every part. So, okay, now let us look at the graph. First of all, you have the exist stress against strain. Okay, stress against strain graph. So there are 5 points along the graph that we're going to look at, which is point A, point B, point C, point D, and point E. You didn't know what happens at every single point. So from O to A, okay, A is what we call proportionality limit. Okay, so it is the maximum, okay, maximum value, maximum stress for which Hooke's law is still obeyed. So OA line, it shows the material obey Hooke's law. Okay, so at point A, that is the maximum limit. Okay, I will call the maximum limit. So once it passed point A, it means object no longer obey Hooke's law. So it's no longer a straight line. So OA is a line that materials obey Hooke's law, and then force is directly proportional to extension. The more force that you have, then the more extension. Okay, it will extend. So when the force is removed, the wire will return to its original length. So this is what we call elastic behavior and elastic deformation. Okay, elastic deformations. So what happens at a point B? So point B is the elastic limit. Okay, it's the elastic limit. So when force is removed, the material will still return to its original length. So it's still part of the elastic deformation. Beyond this point, object will never return to its maximum or to its original length. So it is permanently stretched. So elastic deformation, it ends as point B. Okay, Hooke's law, it ends as point A, but elastic deformation, it ends as point B. Beyond this point, the material will never return. So we end at point B, and the area between two parallel lines, OA and CT. Okay, so we have two lines, two set of a value here. Okay, one is a OA, and another set is a CT. Okay, here is T, here is a C. So the area in between these two lines, it represents the work done to cause permanent extension to OT. Okay, to OT. So once it passed B and it moved on to point C, then object will be permanently stretched. Okay, permanently stretched. So how much is being stretched? Okay, what is the work done that needed to stretch object by this much from O to T? So this is the difference between the initial and the final length. Okay, initially object will go back to O, but if you exert, okay, if force exert point B, if you stretch the object exert point B, then object will be permanently stretched. Okay, so it depends on how much is being stretched. So point T, okay, point T is after you release the object. Okay, so beyond point B, and then when you reach point C, then you release the object. The object, it won't go back to the length O anymore. It will go back to length T. Okay, it will go back to length T. So from O to T, okay, how much work is being done? So it is being determined by the area, okay, by the area between OA and CT, right? So original length, let's say this is a length of O, okay, this is a length O. So from point O to point B, even though you stretch the object, it will still go back to point O. But once it passes point B, then it will go back to length T. All right. So how much work is needed to permanently stretch it? It depends on the area, okay, on the area between OA and CT. That is the meanings of this phrase. Okay, that is the meanings of this phrase. The area between two parallel lines represents the work done needed to produce permanent extension, OT. Okay, permanent extension, OT. So point C is what we call U point. Okay, is what we call U point. So this is a point where plastic deformation start. So the internal structure of the material is start to change because the plane of the atom, they slide across each other. So what happens in an object is now the atom has moved. All right, it's unlike a point A. Point A, you just stretch the object, the atom inside the object, they just become slightly further away from each other. But when it reach U point, when it pass U point, what happened? Now, as you can see in the diagram, the atom, they slide, they move its positions. Okay, they move its position. So the internal structure of the material, they start to change because of the plane of the atom, they slide across each other. And then when the force increase, the extension increase rapidly because now you already changed the shape of the object. All right. So the plastic deformation, okay, start here. Now, what does it mean by plastic deformation? It means the object will never go back to its original shape and also original length. Okay, it won't go back anymore. So point D, okay, now it slides. So at point C, object just, the atom just slides. Maybe it becomes thinner, the whole object. So just like you stretch a rubber band. Okay, when you stretch the rubber band, it becomes a thinner. Okay, dia menjadi nipis. So if you keep stretching it, eventually object will reach point D. Okay, the plastic deformations from point C, if you keep stretching it, it will reach point D. And point D is what we call breaking stress point. Okay, breaking stress point. So stress on the material is now at its maximum value. And beyond this point, the object becomes thin and a neck is being formed. Okay, so this is the neck. So the place where it becomes thinner. And if you keep stretching it, eventually it will break at this point. Okay, it will break at this point because now it becomes thinner, it forms a neck here. So if you keep stretching it, then object will break. And when it breaks, we say it reached point E. That marks the end of the our motion, our stretching. Okay, that marks the end of our stretching. So at point E, the object will break. Okay, at this point, we call it breaking point or fracture point. So that also marks the end of our plastic deformation. Right? So from O to B, it is our elastic deformation. And actually from B until E, that is our plastic deformation. So elastic and plastic, make sure you know which part is elastic, which part is plastic. Sometimes question will ask you to label, okay, and then sometimes question will ask you to explain it. So elastic deformation means object can still go back to its original shape. Plastic deformations mean it's permanently stretched. So this table, it tells you the difference between elastic deformation and plastic deformation. So elastic deformation, extension, it does not exceed elastic limit. Okay, so it's still within elastic limit. So plastic deformations, it exceeds elastic limit. And for elastic deformation, when the force is removed, it will go back to its original length. Whereas for plastic deformation, it does not return to its original length. In other words, we say it is permanently stretched or lengthened. For elastic deformation, it obeys Hooke's law, and plastic deformation, it does not obey Hooke's law. And then for elastic deformation, it does not change the internal structure, and plastic deformation, it changes the internal structure. Now, what does it mean by internal structure? Like the one I showed you just now. Okay, it changed the shape of the atom, all right, as shown in this diagram. So the structure okay, the structure in a plastic deformation is permanently changed. So the atom, it won't go back to its original shape anymore. So when Hooke's law is obeyed in elastic deformation, the energy stored during elastic deformation is fully recovered when the force is removed. Plastic deformation, energy is being converted to heat. So if you take a rubber band, you keep stretching it, stretch, release, eventually you will feel that the rubber band is hot. Okay, that is because part of the energy has been converted into heat energy. And that is one of the characteristics that we use to identify whether object undergoes elastic deformation or plastic deformation. Right? So if you feel heat, then the object is actually undergoes plastic deformations already, because now the incident structure has changed, and not all of the energy can goes back to the can be used to return the object to its original shape. All right, in elastic deformations, the energy will be used to recover the shape of the object, to make the object go back to its original shape. But when it comes to plastic deformation, because object will never return to its original shape, that means there must be some loss of energy. So what happens to the loss of energy? It is being converted into heat, right? It's being converted into heat. So that is what happened in plastic and elastic deformation. So this table you need to know, okay, especially for an objective question, if I'm not mistaken. Because objective questions sometimes will ask you to choose which one belongs to elastic deformation and which characteristic belongs to plastic deformation. So now these tables, okay, this graph, it shows you force against elongations plot. Okay, actually the shape is exactly same as the shape of a stress against strain graph. Okay, stress against strain graph. So the only difference is just the axis. Okay, the only difference is just the axis. So force against elongation. Now you have 4 different materials shows in this diagram. So basically it wants to show you what? It wants to show you the difference between ductile material and also brittle material. So ductile material, object undergoes both elastic and plastic deformation. So means that object, if it hasn't exit the elastic deformation, it can still go back to its original shape. Right? But for ductile material, the material is just have elastic deformation. It doesn't undergo plastic deformation. So a typical example would be glass. So you're given 4 examples right here. Steel, coppers, and aluminium, actually they belong to ductile materials. And then brittle material is glass. So once it passes the elastic deformation, straight away it will break. Okay, it will break. So for ductile material, it has plastic deformation. That is the main difference between them. And then for brittle material, it won't have, okay, it has no significant plastic deformation. So glass, either you break it or not. Okay, it won't change its shapes. So that is the difference between ductiles and brittle material. Okay, now let's move on to 11.2 Young modulus. So Young modulus involve a calculations. Okay, so we have a calculations starting from this point. Okay, the main focus in chapter 11 is actually Young modulus. Now, what is Young modulus? Young modulus is defined as the ratio of a tensile stress. Okay, it's a stress to strain. This is a ratio. So if the proportionality limit has not been exceeded, that is one of the conditions. So mathematically, it can be written as y equals to, well, because we're looking at the ratio of stress to the strain, so we have sigma divided by epsilon. Okay, sigma divided by epsilon. And since we know, okay, in a previous subtopic, we know that sigma is force over A and epsilon is a E over L naught. So when you combine these two equations, okay, what are you going to obtain? Okay, you are going to obtain, you're going to obtain a new equations. So you have y equals to sigma over epsilon. So it is equals to F over A divided by E over L naught. Okay, so rearrange the equations, you flip it over. So Young modulus can also be written as FL naught over AE. Okay, FL naught over AE. So this one at the same time is equals to FL naught over AE. And this is an equation that we use very often in our calculations, okay, compared to sigma over epsilon. Most of the times we use y equals to FL naught over AE. Okay, kebanyakan kerap kita akan pakai y equals to FL naught over AE berbanding dengan sigma bahagi epsilon. Okay, so a Young modulus is a measure of a resistance in deformation. Okay, it measures the resistance of a solid to change its length. So what does it mean? It means if something's with higher Young modulus, then it is harder to change its shapes. Okay, it will be harder for us to change it, to change the length of the object. So when y is greater in the value, it means material is not easily to be stretched or compressed. So this value, we use it quite often in engineering, okay, because you want to know whether an object can change its shapes easily or not. You will see this very often if you're a study engineer. So it is a scalar quantity. So SI unit is kg m -1 s -2 or Newton n -2 or Pascal. So basically the unit is same as the unit of a stress because epsilon is dimensionless. Therefore, the unit that we use for Young modulus same as the unit of stress. So Young modulus, it does not depend on the length, but rather it depends on the material that makes up the wire. Okay, so we have a Young modulus. Young modulus, okay, now you have an object. Okay, this object, it comes with, obviously, it comes with a length, it comes with an area. Okay, this is the area. And then we have the material also. Okay, so we have equations FL naught over AE. Young modulus, it does not depend on the force, it does not depend on the length, it does not depend on the area. Okay, it depends on material of the object. So basically, okay, basically this equation, it won't affect our Young modulus, the value of Young modulus. Okay, the thing that affect the Young modulus is the material. Now, why is it important to know? Okay, why is it important to know that Young modulus depends on material? Because quite often questions will give you two situations. Okay, two situations. So you have an object with same material. Object A, you apply 10 Newton of force. Object B, you apply 20 Newton of force. And then question might ask you what happens, what is the length of the object, or what is the original or the cross-sectional area of the object. So in that case, you have to know that now these two objects, they have same Young modulus because they are made of same material. Okay, so same material means same Young modulus. So Young modulus, it does not depend on F, it does not depend on L, it does not depend on A, it does not depend on E. It depends on just the material. Same material, okay, same material, same Young modulus. Okay, same Y. So it is very important in a calculations type questions because in this chapter questions, they truly like to give you, okay, to give you two objects with same material, then with some difference of physical quantity, okay, some physical aspect, they change it. So Young modulus does not change if the length of the wire increase or decrease. The table shows the values of Young modulus for various objects, okay, for various objects. So this one, you just have to know some the meanings. If you have a greater value, means it's harder to change shapes. Okay, means it is stiffer. Okay, stiffer means harder to change. So greater, okay, greater Y means stiffer. Okay, dia lebih stiff, dia lebih susah nak ubah dia punya shape. Okay, means object is stiffer. So the one with the highest value, the steel, that one is the most stiff, right? Most stiff. So relationship between the force and a constant, between force constant K and a Young modulus Y for a wire. So now we want to look at, okay, because you're looking at elasticity, so we are going to look at the K, okay, the force constant and also the Young modulus. So for a statement, Hooke's law and the definition of Young modulus, this one is Hooke's law. Okay, this one is Hooke's law. Okay. H-O-O-K-E-X. Law, and then this one is coming from Young modulus equation. Okay, Young modulus. So rearranging the equations for a Young modulus, now we have F equals to KE and also F equals to YAE over L. So when you combine these two equations, you obtain a new equations called K equals to YA over L naught. Okay, K equals to YA over L naught. So this means the force constant depends on the types of material, the cross sections, the area, and also the original length of the wire. Right? So we are looking at the spring constant. So actually a spring constant is also known as a first force constant. We use K in an object that can be deformed, okay, that undergoes elastic deformation. So not just a spring, okay, actually K exists in all sort of object. Just that most of the time we use it in spring because that is the most common seen example, right? So K also known as force constant, which depends on the types of the material, it depends on the cross-sectional area and also the length of the wire. All right, so this is just an additional information for you. So the next thing that we're going to discuss is the graph, okay, the strain energy for force elongation graph. So this part, we're going to look at force elongation graph again. So we discuss the strain energy per unit volume from a stress against strain graph. So we want to derive two equations in this topic, okay, in this subtopic. When a wire is stretched by a load, okay, the work done in stretching the wire is transformed as a strain energy, or we say elastic potential energy of the wire. So when you stretch something, it will have restoring force, okay, and the work done to stretch it, okay, it will be transformed into strain energy. So once you release the object, this strain energy or this elastic potential energy will make the object to go back to its original shape. So now what we want to do, we want to calculate the work done. Okay, the work done in stretching the object. So how are we going to calculate it? So we calculate it based on this graph. Force against extension. Basically, it is our FS graph that we have seen in chapter 5. Okay, FS graph that we've seen in chapter 5. So now we have force against extension. The total work done in stretching the wire from 0 to E is given by the shaded area. Okay, so if you integrate FDE, then you will obtain W equals to 1 over 2 FE. Okay, 1 over 2 FE, which is the area under the graph. Okay, area under the graph. Oh yeah, one more thing here. You have another new symbol. Okay, another symbol, not W. So most of the time we use a U. Okay, not new symbol, but we are supposed to use U when it comes to energy. So work done is equals to energy because work done is being transformed into elastic potential energy. So work done and elastic potential energy in the object, they are the same. Okay, they have the same magnitude. So W equals to U, which is equals to 1 over 2 FE. Okay, 1 over 2 FE. So it is the area under the graph. It is a shaded area in a diagram. Okay, so work done equals to the energy in an object, which is equals to 1 over 2 FE. So now from the definitions of a tensile stress and a tensile strain, there's the tensile stress, sigma equals to F over A, F equals to sigma A. Tensile strains, we have an equation for stress, equation for strain. So now we sub it into the equation. Because we have F and we have E, so we want to see what happened when we sub F equals to sigma A and elongation equals to epsilon L into the equation. So you sub both of them into the equations, you will obtain U equals to 1 over 2 sigma A epsilon L naught, which is then equals to 1 over 2 epsilon sigma and then AL. Now AL, when it comes to a rectangular shaped object or a cylinder, then it also represents the volume. Okay, it also represents the volume. So we have an object, for example, this is our road. Okay, so when you pull an object, okay, when you exert the force on an object, so this is our cross-sectional area. Okay, cross-sectional area is the area that we use in our calculation. This is our A. So remember, force is always perpendicular to the area. Okay, force is always perpendicular to the area. So you stretch the object, and then this is the length. So cross-sectional area times length, actually it gives us volume. V equals to AL naught. Therefore, U can also be written as 1 over 2 sigma epsilon V. Okay, sigma epsilon V. So remember, F is always perpendicular to the area. So what does it mean? Now, I give you an example. Why students always got it wrong in this sort of example? Sometimes force is not being exerted on a small area of the object. Sometimes maybe you have a large surface area, okay, and then a very thin height here, a very small height here. Okay, so when it comes to this object, okay, when it comes to this object, if you exert a force on a large surface, on the big surface, okay, if you pull or stretch an object along on this surface, then the cross-sectional area that you should use in calculation is this surface area, okay, the last surface area. And where is the L naught then? L naught is now the height of the object. All right, L naught is now the height of the object. So you look at the directions of the force. You look at the positions of the force. Okay, force always perpendicular to A. So after you identify the directions of the force and also where is the A, then you should be able to determine where is the L. Okay, L is always the same, it's always parallel to the force. Okay, so kamu kena tahu macam mana nak tentukan A dengan L. Okay, so untuk example yang kedua ini, for the second example, students always got it wrong. Okay, because you are so used to small cross-sectional area compared to the large cross-sectional area. Okay, so yang penting kamu kena tahu manakah F, manakah L, manakah A. Okay, so yeah, well, last part, you see, we can finish within half an hour. That's why I told you this is actually just a very short topic. Okay, everything is all about memorization. You just memorize what is the elastic deformation, what is plastic deformation, what happened at every single point along the graph. Okay, and then you know how to apply the equation for stress, strain, Young modulus, and the last one that we're going to see right now is the strain energy. So strain energy is the product of area under the stress strain graph. So just now we have force elongation graph. Now we have stress against strain graph. Okay, stress strain graph. So strain energy U is equals to area under stress strain graph times the volume. Okay, times the volume. So U is equals to 1 over 2 and then sigma epsilon V. And based on this diagram, we have U over V equals to 1 over 2 sigma epsilon. Okay, sigma epsilon. So stress against strain graph, if you rearrange the equations that you obtained above, U equals to 1 over 2 sigma epsilon V, you rearrange it, then you obtain an equation, U over V equals to 1 over 2 sigma epsilon. And that actually represents the area under stress strain graph. Okay, stress strain graph. So basically, what have we learned in this chapter? Okay, in this chapter, wait, yeah, let me go back again. So I'm going to do a quick summary with you guys. So what have we learned? what have we learned in this chapter? Okay, we learned about stress and strain. Okay, we learned about stress and strain. Okay, so stress, it tells us the force over area. Okay, it is the ratio of a force over area. So stress, the symbol is sigma. Okay, sigma equals to force over area. And now when it comes to strain it just tells us the degree of deformation. So which shows us the change in the length, the ratio of a change in the length over L naught. So when you combine these two equations, it gives you something called Young modulus. Okay, it gives you something called Young modulus. So Young modulus, it tells you the stiffness of the object. Okay, it tells you the stiffness of the object. So if you have a higher Young modulus, the larger Young modulus means object is stiffer, it's more stiff. Now, what does it mean by stiffer? Stiffer means it's getting harder to change its shapes. So the equations that we use in Young modulus is so the equations that we use, okay, the equations that we use in Young modulus, y is equals to sigma over epsilon, okay, which is also equals to FL naught over AE. Okay, FL naught over AE. But the important thing in this equation is you have to know F, okay, directions of F always, okay, always perpendicular to A. Okay, always perpendicular to A. So this is the equations that we have to know. So now done. Okay, basically that is the equations that we have in this chapter. And then from here, okay, from here we know a new terms from the derivations of the graph. Okay, we get a new equations called strain energy. So once you know the Young modulus, you know the characteristics of the object, you know whether it is easy to deform or it is hard to deform, then we try to calculate elastic energy inside the object itself. So elastic energy, we have U equals to, okay, U equals to 1 over 2 Fe. So we calculate the energy stored in the object. We calculate the work done to stretch the object. So the amount of work done that you exert on the object, it is equal to the amount of elastic energy in the object. Once you remove the work done, when you remove the force, the elastic energy will makes the object go back to its original shape. Okay, original shape. So from this equation, okay, from these equations, we managed to sketch a graph. Okay, actually we derive it from the graph of F against E graph. Okay, F against E graph. So area under F against E graph, that is our U. Okay, area under the graph. Area under FE graph, that represent our U. So from area under FE graph, okay, from area under FE graph, we obtain energy. And then from energy, if we expand these equations again, okay, we expand this equation by using sigma equals to F over E, rearrange the equation, F equals to F over A, sorry, and then F equals to sigma A, and then one more thing, we have a epsilon equals to elongation over L naught. Rearrange it, we have a elongation equals to epsilon L naught. So if you sub these two equations into equations for energy, eventually we will obtain a new equation, or U equals to 1 over 2 epsilon sigma times AL naught. Okay, times AL naught. So this equation, if you simplified it, then it will become U equals to 1 over 2 sigma epsilon V. Right? So if you rearrange this equation, then what is going to happen? Then you will obtain a new graph. Right? So if you simplified it, you have 1 over 2 sigma epsilon V. So from this equation, you rearrange it, you will obtain U over V equals to 1 over 2 sigma epsilon. Okay, so from these equations, once again, we are going to obtain a new graph. Okay, we're going to get a new graph called sigma against epsilon graph. Okay, sigma against epsilon graph. So area under this graph, okay, area under the graph, it is equals to U over V. Okay, U over V. So done. Okay, that marks the end of this chapter. So what you have to know is all this equation, and of course, okay, of course, the graph. Okay, of course, the graph. So you have a force, not force, okay, sigma epsilon. Sigma against epsilon graph. Okay, sigma against epsilon graph. And then the shape of the graph. Initially, it is a straight line, and then it becomes a bit of curve when it goes from B to C, and then it is a big shape like this, and then it breaks. So you need to know where is plastic deformation, where is elastic deformation. Okay, you have point A, point B, point C, they are all located at here, and then point D and point E. Okay, so you need to be able to explain this shape. So basically, you just memorize this page, okay, this whole thing. So this whole thing, together with the summary above, that marks the end of chapter 11. Right, that marks the end of chapter 11. So I think that's it. Okay, that's all for today. So if you're done, if you don't have any questions, then you may leave the class. Right, so next week we'll continue with chapter 12. So kita dah siap dengan chapter 11. Chapter 11 actually dia pendek sahaja. Benda pun tak banyak, equations pun baru berapa? Baru 3 atau 4 sahaja. Okay. So I think that's all for today.